Hello everyone and welcome to the course on Herbal Product Technology and Regulatory Sciences. In this week we are learning different herbal formulations. We saw that we cannot consume herbs per se sometimes, and sometimes due to the occurrence of raw material it makes them difficult to formulate. So in this case, many a times owing to the bioavailability issue, we resort to different formulation techniques, and as a result in this week we saw different novel drug delivery system such as liposomes, the modified liposomes also called as phytosomes. In this session we will see one more add-on modified liposome derivative, and that is your ethosomes. So what are ethosomes? So ethosomes are basically bilayer vesicles, a way very similar to that of your liposomes, in a way that they contain phospholipid bilayer. So this bilayered vesicles are often as small as 30 nanometer in size and may be as large to several micrometers in size. Now they are called as ethosomes. The word etho comes from ethanolic, and sometimes they are also referred to as your ethanolic liposomes for their content of ethanol. So in terms of their composition, they definitely contain your plant bioactives, be it the phytoconstituents or it could be the plant extract in entirety. The bilayer is made up of phospholipids, example like your very simple phospholipids like your phosphatidylcholine, which makes it very biocompatible polymer and cell membrane like structure, and in addition to that, along with water, they also contain alcohol, that is ethanol. Now what is the role of this ethanol? The ethanol in your liposomes, more specifically the ethosomes, are drug delivery systems in which ethanol performs the function of solubilizing the phytoconstituents which were otherwise sparingly soluble either in the water phase or in the lipophilic phase, whereas most of the compounds like your flavonoids are mid-polar in nature. Your ethosomes, the ethanol act as solubilizing agent. Not only that, your ethanol also enhances skin permeation. So definitely this type of drug delivery system in herbal scenario is mostly applied to transdermal drug delivery in cosmetics, but in some cases nowadays they are also consumed internally. So what is this little difference between the liposome, what we saw previously, those are the phytosomes, and ethosomes. So if you go to see liposomes, liposomes are the simplest or mother of all this drug delivery forms, in which you have a phospholipid bilayer. You can see clearly these are the polar heads as well as these are the non-polar chains. Now these are the polar heads and these are the non-polar chains. So when this bilayer fold to form spherical structures, we call them as liposomes. In liposome essentially you will find lipophilic compounds within the lamellar structure, that is within the bilayer hydrophobic chains of the phospholipids, whereas you will find the polar molecules within the very polar core, and this core is actually a sphere which is made up of polar heads of phospholipids. So most of your hydrophilic drug moieties or phytoconstituents will lie inside the core. Now when we moved on to your phytosome, you recollect here in this case, in addition to this, you form a strong association. That is, the phytoconstituents can actually form a hydrogen bond with the polar head of your liposomes. So in this case, when the liposomes form a hydrogen bond kind of association, the bond is chemically linked, and what happens here is your molecules stick or associate with the polar heads. So most of your phytoconstituents which can associate in form of a hydrogen bond association, You will find them located on the polar head. Now what happens in ethosomes? In ethosomes, because of addition of ethanol, what you will see, there's a little difference in core that occurs. Instead of a principally aqueous core out here, you will see the core here is aqueous plus alcohol. So you will see essentially a hydroalcoholic core, and that increases the solubility of midpolar compounds. Now in addition to that, some alcohol molecules also get associated here, and they work in order to solubilize the compounds on the lipophilic side, as well as they act as permeation enhancers by perturbating the phospholipid bilayer. So what exactly are the components of ethosomes and how are they made? Let's study the components first. So in this case, the components of ethosomes are very similar to that of your liposomes. That means they contain phospholipid principally somewhere between 0.5 to 10% by weight, and they are composed principally of glycerophospholipids, sphingomyelins, some things as simple as your soy lecithin, egg lecithin, and so on. Now in addition to that, very similar to like your liposomes, you might also have sterols incorporated, which include your cholesterol and sitosterol for enhanced stability. And here comes the important component. The important component of this drug delivery system, ethosomes, is your ethanol. The percentage of which depends on the different references, may vary somewhere between 20% to 45% by weight. Now this ethanol gets into the core, as we saw, as well as in between the phospholipid bilayer, where they act as excellent solubilizing agents for phytochemicals, for extracts, as well as permeation enhancers. Now in certain cases, what happens is, if you say ethanol, ethanol is a very volatile liquid. So when you have a contact with ethanol, due to body temperature, the liposomes get heated, the ethanol might evaporate. Same thing happen during the processing as well as during the storage. So in order to decrease the volatility of the ethosomes, some component of your ethanol might be replaced with a little lesser volatile ingredients, such as your propylene glycol. Now propylene glycol renders your ethosome soft. It makes it more biocompatible. What happens is, certain times when ethanol is involved, it might cause an instant cooling, it might cause a skin irritation, whereas PEG is a very more nascent and a very stable ingredient, which increases the viscosity, which maintains the softness, as well as decreases the volatility. In some cases, it might be replaced with isopropyl alcohol as well as glycerine or glycerol in order to reduce the volatility of the ingredients. In some cases, when you want more permeation, you might add permeation enhancers. In such cases, this permeation enhancers can also include your surfactants such as your twins and spans, and certain cases even bile salts have been added. So components of your ethosomes principally consist of your phospholipids, sterols, ethanol, which is the major percentage, definitely water or an aqueous media. In addition to that, the substituents for your ethanol in some cases, which include your propylene glycol, isopropyl alcohol, glycerol, as well as in some cases permeation enhancers like your surfactants. In some cases, you might even have components such as your transcutol being added. So what are these different types of ethosomes? Ethosomes can be classically divided into 5 categories. So the very first category is your classical ethosomes. So what happens in case of classical ethosomes is, we'll just take this little small portion and call it the classical one. So in classical ethosomes, you have a phospholipid bilayer, you have an aqueous layer, you have an oleaginous layer. Depending upon the solubility of your drug might sit into any layer, but you have ethanol also being added. So this red color particles, you can imagine it to be your ethanol, or we can just write it as your E's. So this ethanol also makes its way into the phospholipid bilayer. So in classical ethosomes, you have your ethanol being there. Now in some cases, this ethanol, like I said, in order to decrease the volatility, may be replaced by other alcohols. So this other alcohols, or when there is a mixture of two alcohols, you call it as binary ethosomes. So let's put here as binary. So in this case, what happens is, in addition to your ethanol, you might also have something like a propylene glycol. So I am just drawing a little different structure. The ratios of propylene glycol, ethanol may vary. So you have different components like your ethanol, propylene glycol, which might be fitting in different areas of your ethosomes. In some cases, there might be permeation enhancers which are added, like your surfactants. In such cases, they are called as trans ethosomes. Now this trans ethosomes may have components such as your transcutol. It might have your surfactants. This include your tween, span, etc. as well as your bile salts. A number of other permeation enhancers might also be added, and in this case again you will see your ethanol being there dispersed in both aqueous as well as organic phase, along with some amount of your surfactants making their way through the bilayer as well as sometimes into the matrix as well. In some cases, what happens is the stability of this bilayer is enhanced by addition of what is called as hydrogenated fatty acids, or phospholipids containing hydrogenated fatty acids. Now many a times when you talk about lecithin, such as soy lecithin, egg lecithin, it contains a phosphatidyl group as well as fatty acids, and many times these fatty acids may be unsaturated. An unsaturated fatty acid, say for example, this is a very saturated fatty acid, but when I am talking about an unsaturated fatty acid, many a times disturbs the symmetry and creates instability. So in order to ensure more stability, what is done is this phosphatidylcholine or many of these phospholipids are hydrogenated, and then maybe 1:1 ratio of your phospholipid is to a hydrogenated phospholipid is added. This gives more strength and a better structure to the ethosomes, and such kind of ethosomes where phospholipids, the fatty acid chains, are more saturated, they are called as your composite phospholipids. So again you will have your ethanol everywhere, but here your fatty acids are more of a saturated fatty acid. So these are your composite ethosomes. The last case, you will see that many a times functionalization is carried out, and this functionalization is carried out in order to retain certain antibodies, in order to retain certain binding proteins, or any of the molecules or charged molecules which are there. So you will see different moieties being added, and this moieties are achieved, or this moieties are being added to achieve specific target. So you know this antibody will go and bind to a specific region, some targets or some charges are associated with it. So such kind of functionalized phospholipids are prepared, and that type of ethosomes are called as your targeted ethosomes. So you might have classical, binary, where you have two alcohols, trans ethosomes which are more permeable, composite which are more stable, and targeted which helps you achieve a very targeted drug delivery of your molecule. So how are the ethosomes prepared? So how are these ethosomes prepared? So ethosomes are prepared by different methods. The most common method is what is called as cold stirring method. In a very cold stirring method, what you have to do is you have to take aqueous phase. This generally contains water, in certain cases buffer, or in certain cases even saline. If the drug is water soluble, it is solubilized into aqueous phase. If the drug is organic soluble, that is a lipophilic drug or a lipophilic phytoconstituent, it is solubilized in organic phase made up of your phospholipids, surfactants and ethanol. Now what is done is this aqueous phase is slowly added to the organic phase in a very fine stream at a very slow rate, or just like 1 to 200 microliters a minute. But the stirring is very vigorous. So a very thin jet of aqueous phase enters the organic phase at a very high RPM at about 30 degrees Celsius. Now this is done for about 5 to 30 minutes, and you get what are called as your cold ethosomes. As opposed to that, there is second method which is called as hot method, in which the phospholipids, instead of dispersing in organic phase, are heated in water phase at 40 degrees Celsius. So this phospholipid dispersion in water is then mixed with ethanol or probably propylene glycol or mixture of both and sonicated vigorously. Now what happens is, during sonication process, this phospholipid layer breaks and the ethanol PEG kind of enters in, and you get a particulate formation which is called as your ethosomes. You can also resort to conventional method like your ethanol injection method, because here we want the ethanol and that's your ethosomes. So organic phase basically consists of the same phospholipids, your drug moieties if they are phospholipid soluble or organic soluble, surfactants and ethanol are injected in the aqueous phase, reverse from the cold stirring. Here the organic is injected into aqueous phase and homogenized with an ultrasound, that is your ultrasound probe, for a period of 5 minutes. Now this may be pulsatile. So 5 minutes you have an ultrasonication, 5 minutes rest, again 5 minutes ultrasound. So these pulses are given eventually to size reduce it, and what you get at the end are your ethosomes. You can also resort to again a method of preparation of liposomes, if you recollect, a thin film hydration method, where you take your organic phase which is made up of your phospholipids, it is made up of your surfactants, sterols and other lipophilic moieties, which is kept in organic solvent and then evaporated, and later on an aqueous solution is added. Here instead of aqueous solution, you add a hydroalcoholic solution to reconstitute the liposomes and you get your ethosomes. There are different other methods which are also there, which include your pH gradient method. In this method, what is done is a liposome containing drug, that is a empty liposome is prepared, and in this empty liposome you have a core which is a acidic pH, say for example, and then you have a outer aqueous media which is at basic pH. Now what you will do is you will mix the drug in the outer aqueous layer, now which might be in unionized form, and then which will get absorbed into the acid layer slowly as you keep it for equilibrating. So pH gradient method is also there, and there are many other numerous methods, but the most abundant one is your cold stirring method. Now once your ethosomes are prepared, we need to size reduce it further. Now the advantage of ethosome is because of the charge of ethanol comparatively as compared to your liposomes or phytosomes. Normally the particles or the ethosomes that are formed are much finer because of the charge stabilization by your ethanol. That is a good zeta potential, and as a result, but still a good size reduction can be done by different methods we saw previously. This includes treating or pulsating with an ultrasound probe, generally at about 43 to 480 kilohertz frequency range, or you could press and extrude it through the membrane filter in a very similar way to that of your liposome with a defined pore size or defined apertures. Not only that, you could use your high pressure homogenization method, which uses a really high pressure up to 1500 bars, that is up to 150 megapascal, and pass it multiple times, up to 3 to 10 times. The more you pass it, the finer it becomes, and these finer particles are then treated as your ethosomes and kept stable. Now once these ethosomes are prepared, they could be stably formulated in form of creams or gels. So you get those ethosomes, now you add polymers. So if you want to prepare a gel, you might add something like a carbopol to this aqueous mixture and then cause gelling, or you could use a cream base and these ethosomes are stabilized in cream base. This is generally done to prevent evaporation of alcohol, because ethosomes, if you keep it as such at ambient temperatures, gradually the ethanol starts evaporating. So you need to take care of it, you need to take care of its stability. So once you have the ethosomes, how do you do the quality control? You would see many of these quality control methods match to that of your phytosomes. That is, once you have your particles being prepared, that is your ethosomes being prepared, the ethosome size can be easily measured by dynamic light scattering. So more is the scattering, the finer is the size, because if you recollect, that is attributed to the Brownian motion. So finer particles have more Brownian motions, as a result they will move more and they will cause lot more scattering as compared to the larger particles. You could also use microscopes, but you need a really ultra fine microscopes like your scanning electron microscope or transmission electron microscope. Now scanning electron microscopes and TEMs use electron beams, and as a result, which will give you a very nicely resolved images up to few angstroms in size. Now in order to ensure stability and a good resolution, what is done is this microscopy is carried out in the frozen state, which is called as your cryo-TEM. Certain cases you can even use probes such as atomic force microscopy, where your carbon tip kind of ensures a good size and accuracy. Now the stability of your ethosomes depends on the zeta potential and the surface charge. So you can do that by checking electrophoretic mobility. So negatively charged particles will move to positively charged electrodes and vice versa. DLS also gives you a fair degree of idea about the potential, because the Brownian motion for similar charged particles would be more repulsive. You can also do what is called as photon correlation spectroscopy. Now in order to ensure or check the lamellar nature, you can do what is called as cryo-TEM, or you can do a protein, you can do a phosphor, like your phospholipids contain phosphorus moiety. So that phosphorus moiety, if you use a labeled one, you can do what is called as a P31, or you can depend on the isotopic abundance of P31 and carry out the NMR. The phase behavior, the transition or glass transition temperature, the interaction of ethanol with phospholipids can be studied by different techniques, which include your X-ray diffraction, which sees the scattering of your X-rays based on Bragg's equation. You could do differential scanning colorimetry, where you see a exotherm or endotherm, whether it absorbs or emits what is called as heat, which is then captured. or you could do a thermogravimetric analysis, which will see the difference in weight at different temperatures, gradually increasing the temperature. Not only that, an important criteria is encapsulation efficiency. Now, whenever you prepare your ethosomes, you want more and more drug to be trapped inside the ethosomes. So, this is checked by first centrifugation, and then this kind of ethosomes are broken up. Dialysis is carried out so that the drug particles are carried out into buffer, and then using HPLC or any analytical techniques, which is very sensitive, you can determine how much drug was encapsulated. Now, for ethosomes which are used for topical preparation, you also see the skin permeation studies, which have been nowadays carried out using near IR or IR spectroscopy, as well as your NMR spectroscopy, generally relying on CH2 kind of associations or bands or their behavior with respect to interaction and without interaction. Now there are few, let's compare the advantages and limitations of ethosomes. The advantages of ethosomes can be all attributed to the addition of ethanol. We call it as ethanol effect. So once you add ethanol to your liposomes, they are called as ethosomes, and this ethanol makes the liposomes more soft, more fluid as compared to the stiffer ones, and this fluidity is good because now your phosphatidylcholine is no longer stiff, it is kind of almost solubilized and fluid. So now your vesicles are also soft, they are flexible, and as a result, because of their softness, flexibility and entrapment of ethanol molecule, your drug permeation is improved. Now the ethanol enhances its intracellular permeability as well as intercellular permeability, and as a result they are much more bioavailable. Not only that, ethanol is also responsible for enhancing the stability. So it has good stability. Now once you have good permeation and good stability, definitely you can work towards reducing the dose. So ethosomes required much less dose as compared to other drug delivery forms, and as a result are less toxic. They are definitely biodegradable because ethanol is considered as a much like native solvent or an organic native solvent, which can be easily produced using greener methods. And last but not the least, once you have your ethosomes ready, you can easily formulate them into gels or creams. Now, but yes, as compared to advantages, we also see certain limitations with ethosomes, and few of these limitations include poor yield. Because of alcohol, certain times there might be a skin irritability, but as we discussed previously, this irritation can be decreased by addition of glycerol, by addition of propylene glycol or even IPA. So this irritancy can be managed to certain extent, but yes, when you are talking about drug delivery system, this requires a very controlled temperature, controlled conditions and environment, which lead to high production cost. High temperature instability is another issue because your ethanol will volatilize, your phospholipids cannot be subjected to higher temperature, and as a result there will be loss in the lamellar structure. So you cannot really subject it to a very high temperatures across or more than 80 degrees Celsius, and then definitely because of alcohol you will see that volatility is much more, but definitely the stability enhances as compared to liposomal particles, but as compared to other drug delivery system you can say it's poor and they tend to aggregate and they leak. Now this is like I said compared to other drug delivery system, but as compared to your liposomes, your ethosomes are much more stable. For ethosomes, still scale up it's a challenge because when you want to do a particle size reduction, you want to do a number of passes, this cannot be done on a large scale because it overtly kind of clogs the membrane, gives a huge back pressure, and still better methods need to be done. But as liposomes are entering in the market with HPH, definitely this is made little manageable. So let's see few applications. So few examples on applications of herbal ethosomes. Ethosomes of ammonium glycyrrhizinate, which were actually evaluated on humans as a clinical trial. It showed that the ethosomes have a very, or did possess a very good anti-inflammatory activity, a good skin permeation even in the cases of skin erythema, as well as skin tolerability. Now the next case for apigenin, where it was more tried out in animal models, there especially for skin inflammation, which was induced by UVB radiation. In that case, ethosome showed a nice skin targeting for COX-2 enzyme, which were mediators. Now, in addition to that, your curcuma longa extract was tried and it showed a good skin hydration, good maintenance of sebum content, and as well as improvement of skin properties. In cosmetics, a clinical trial was also carried out with ethosomes possessing hyaluronic acid. In some cases nowadays, hyaluronic acid is also used as a permeation enhancer. So much so that this is observed that when hyaluronic acid was added to ethosomes, the enhancement in penetration was found to be like 5-fold as compared to your PBS buffer. So here are a few references to ethosomes. So with this, in this week we have studied formulations, the need of formulations, classical herbal formulations and newer formulations, that is your novel drug delivery systems for herbals consisting of your phospholipid drug delivery or phospholipid as a component, which includes your liposomes, phytosomes as well as ethosomes. So thank you everyone for your patient listening.